you want. Awesome. Alrighty, so we're going to do the same basic thing. We don't really have to do much in the way of adjustment, just move that 3 over to the other side. So that's a really quick, easy process. 2 pi x over 3 equals -1. And then just like we did in the previous question, I'm going to do two things sort of simultaneously, or like one straight after the other. I'm going to find that reference angle, which in this case, like the value of tan that gives a value of like either positive or -1, depending on the quadrant, would be pi on 4. And on the same note, I'm going to switch the color again, just so it's really easy and clear for you guys. And I'm going to start adjusting this domain. So I've got x, but I want 2 pi x on 3. It doesn't matter how many steps you do this in. If you are comfortable like multiplying the whole thing by 2 pi on 3, that's great. You need to break it down a little more, also great. I'm going to break it into just like 2 simple steps. And first thing I'm going to do is I'm going to multiply by 2 pi so that you get 2 pi x. And that gives 0 because 0 times anything is 0. And 3 pi on 2 times 2 pi. Okay. That's going to give us 6 pi squared on 2, which is not particularly fun, but we can do it. Okay, we can definitely deal with that. Or better yet, three pi squared. So then we go a little bit further and we divide by 3. So 2 pi x over 3, 0, and pi squared. And we're good to go. Okay, this is not too painful. So if you need any context, for example, just think about the fact that, you know, pi squared is probably approximately equal to 10. I mean, it's 9 point something, something, something. Let's say 10 for argument's sake. The point is you just need some context here. What is important is the fact that you know your boundaries for 2 pi x over 3, because that's what we're going to be working on. Okay, the fact that the numbers get more or less complicated really shouldn't detract from your method. So try not to be intimidated by things like a pi appearing where you didn't have one before, okay, or getting something squared where you didn't have it before. These are all things that you've dealt with in the past quite comfortably. You've been dealing with them for years. And the fact that they're now appearing within methods problems shouldn't change your overall system, unless it's like all of a sudden an x instead of a number. Obviously, that's changing from like a cold hard constant to an algebra system. But the difference between, say, a 3 and a 5 on 2 is for you guys nothing now, right? And the same theoretically, and I know this is an ideal, but theoretically should be the same for you guys if you're dealing with more complex numbers. The difference between pi and pi squared in the concept of all of the things that you've learned at this point, not that big a deal. So don't be too intimidating when you start to see things that like you maybe don't recognize. Anyway, we have our reference angle, so we can keep going. We need to think about the circle, okay, because we want tan to be negative. Okay, so I know that you guys are quite comfortable reading the circle right now, so I'm just going to move along to show you which quadrants it would actually be in. So we've got one quadrant, which is pi minus the angle, and we've got the other quadrant, which is 2 pi minus the angle. So we'd be looking at, so 2 pi x on 3 is equal to pi minus pi on 4, and 2 pi minus pi on 4. Now, aside from the fact that the numbers were a little bit full on, did everything there make sense?
Yeah.
Awesome. Fantastic. Alrighty, cool. Let's keep pushing then. So we've got 2 pi x on 3. I'm going to simplify these down and then also work on finding any other solutions that might be in there. So we've got 7 pi on 4. Now, this will require a little bit of just thinking about whether a value is greater than or less than or something along those lines, because we need to think about the case where values might be outside the domain. So we know that our domain is between 0 and pi squared, because remember, we're going to use the adjusted domain. Now, first question. Are both of those inside the domain? And if you don't know what's causing you trouble. Yes? Awesome. Okay, cool. Are you confident there?
Not 100%.
Not 100%? Okay, that's fair enough. That's completely fair enough. Okay, let's have a think about it from a logical point of view then. Are they both greater than 0?
Yeah.
Okay. Now, pi squared is tricky, but if we think about it in terms of numbers, let's just break it down for argument's sake. Let's say that pi squared is 9, because we know that pi is a little bit greater than 3. Is that fair for just the sake of visualizing?
Yeah.
Awesome. Okay. Now, we have to think about the fact is 3 pi on 4 bigger than 9?
No.
No, it's not, because it's less than a whole pi. It's not even one whole pi. It's 3/4 of a pi.
Yeah, I think about it in whole numbers. So 7 pi on 4 is close to 8. So 7 times 3.
But 7 on 4 isn't close to 8. 7 on 4 is close to 2.
Yeah, that's what I mean. Like, it's close if I go 8 pi on 4, I can see that that's 2.
Oh, yeah, that's exactly it. This is what I'm talking about. That's perfect.
Yeah.
That's exactly what we need to be doing. We need to just be thinking in terms of comparisons. So, Awesome. Both of these are inside the domain. Let's start pushing the boundaries, because we know that we can add 2 pi to these to get more sets of solutions. We're just not quite sure if they'll be inside the domain or not. So if we add 2 pi to the first, like 3 pi on 4, we're going to get to 11 pi on 4. And while we're here, we'll do the second one too, which is 15 pi on 4. Now we need to start thinking, are these ones most likely inside the domain? Now, 11 pi on 4. What do you think about that?
Closer to 3.
It's closer to 3, yeah. So 12 would make it 3, right?
Yeah.
Okay, so it's less than 3?
Yeah.
Awesome. So you've got something that's less than 3 multiplied by pi. Is that going to get over pi squared?
No.
Nope. So 11 pi on 4 is good. What about the 15?
Well, that's close to 4, so...
It's very close to 4. Yeah, very close to 4, and then times it by 3, you end up at 12. So that one's not in. That one doesn't make the cut. It pushes past that boundary. Now, there are actually ways to prove this, but we've done it entirely by inspection, and I have some good news for you. In a calculator-free scenario, you wouldn't be asked this question anyway. Okay? I wrote these questions to challenge and push the boundaries of what students were working on. And I pushed them past what the curriculum demands in some of the hardest questions, like this one. So the question itself is not that hard. The domain is. That's what causes the complication. So the good news is this is actually harder than what you have to deal with in the class. So just by doing this here with me, you're actually ahead of where you're supposed to be, which is awesome. Now, if that has gone past the boundary, does it make sense that we don't have to keep looking because we're only just going to keep getting further and further past the domain?
Yeah.
Sweet. So we can stop there. We can call it a day. We've got 3 solutions. All we need to do now is that final bit of rearranging. So I'm going to multiply both sides by 3, which will get rid of that 3. So now I'm looking at 9 pi on 4, 21 pi on 4, 33 pi on 4, and then I'll stop. And then I'm going to divide both. Actually, I'm going to cheat. I'm going to divide both sides by pi, which is quite literally going to do that, nice and easy. And then I'm going to divide both sides by 2. So I'm going to be left with x equals 9 over 8, 21 over 8, and 33 over 8. And there we go. We're good. We've got our 3 solutions. They fit quite nicely inside the domain, realistically. If we have a think about this, 3 pi on 2. Oh, actually. No, we're fine. 3 pi on 2, so pi is obviously 3, and 3 over 2 is like 1.5. So 1.5 times 3 is roughly 4.5. Ballparking here, just for context sake, obviously not accurate. Roughly 4.5. 33 on 8 is only slightly over 4, because 32 on 8 would be exactly 4. So you can see that all three of your solutions fit really snugly inside the domain, without you even actually trying. That was just a result of you altering the domain and then following that through the whole way. How's that look to you guys?
Good, thank you.
Awesome. That's awesome.